Hi everyone, welcome to Unit 13 of online course on probability distributions. In this unit, we are presenting generating functions of Poisson distribution. Generating functions in that case, in the family of generative functions, we are deriving probability generative function, moment generative function, cumulative generative function of Poisson distribution, and how we are using moment generative function or cumulative generative functions for obtaining moments or cumulants of the distribution. And generative function, probability generative function, by definition we know it is P x of s is equal to expectation of s power x. You know the probability generative function P x s, that is defined as expectation of s power x, where s is a real number quantity. And for the Poisson distribution, probability generative function is derived as this P x s is equal to expectation of s power x, and that is sum over x s power x f of x. Since x is a Poisson random variable, f of x is equal to e power minus lambda power x divided by x factorial, where x is equal to 0, 1, 2, etc. So, this is our Poisson probability mass function, and in order to find the probability generative function of Poisson random variable or Poisson distribution, you substitute f of x here, and that is sum over x s power x e power minus lambda power x divided by x factorial. And this expression can be written as sigma over x is equal to 0 to infinity. This s power x and lambda power x combined together, you can write this as e power minus lambda into lambda s all power x divided by x factorial. So, that is you are combining this s power x and lambda power x, and you write lambda s power x, and from this you take e power minus lambda outside the summation sign. So, e power minus lambda x is equal to 0 to infinity lambda s power x divided by x factorial, and this is a standard infinite series for which you know the value is equal to e power lambda s. So, this is equal to e power minus lambda into e power lambda s. Combining the factors e power minus lambda plus lambda s, that way you can write this expression, or that is e power lambda into s minus 1. So, for a Poisson distribution, probability generative function is given by e power lambda s minus 1. So, that is a probability generative function. As I mentioned, this function is used for generating probability values. If you are considering this probability generative function, and suppose you are expanding this function, and you can find the probability values from the infinite series by identifying the coefficient of s power x. Similarly, we are finding the moment generative function of the Poisson random variable. As we know, moment generative function is defined as m x t is equal to expectation of e power t x. mxt, this is our definition of the moment generative function, and how we are getting the value of the moment generative function of a Poisson distribution, and that is moment generative function mxt is equal to expectation of e power t x, that is equal to sigma over x e power t x f x, and now you are substituting f x value, that is the Poisson probability mass function value, that is e power t x e power minus lambda lambda power x divided by x factorial, and that is equal to again this e power t x, we have e power t x and lambda power x, these two values you have, and that are combining, you can write this as lambda e power t all power x. So, lambda, this is, these two factors are taken together, you will get the value lambda e power t or power x. Substituting, and e power minus lambda is taken outside the summation sign, you have e power minus lambda sum over x lambda e power t or power x divided by x factorial. Again, this is a non-series for us, and the value is equal to e power lambda e power t, because we have sigma lambda power x divided by x factorial, this is our e power lambda, and from this instead of lambda we have lambda e power t. So, this is e power lambda e power t. Combining, e power minus lambda is taken here, and this is e power lambda e power t, and so this is you can write as e power minus lambda plus lambda e power t, or that is equal to e power lambda into e power t minus 1. So, this is a very important function as far as Poisson distribution is concerned, that is the moment generative function of a Poisson random variable, moment generative function of a Poisson random variable is given by e power lambda e power t minus 1. And if you want, you can find the characteristic function also phi x t instead of moment generative function. Actually, our definition is moment generative function is m x t is equal to expectation of e power t x, and but characteristic function is given by expectation of I into t power t x e power I t x, and this is equal to, earlier we have e power lambda into e power t minus 1 is the our moment generative function, we have derived this one. Similarly, you can derive the characteristic function, this is e power lambda, instead of e power t we have e power I t minus 1. So, that is our characteristic function of Poisson distribution. And before giving the Coumadin generative function, let me discuss how we are finding moments of the Poisson random variable using the moment generative function. Suppose you are having the x is a Poisson random variable with a parameter lambda, and we have derived m x t, that is e power lambda into e power t minus 1. This is our moment generative function, and how we are finding the rth arbitrary moment. You know, rth arbitrary moment can be obtained using the moment generative function by differentiating the moment generative function r times with respect to t and put t is equal to 0. So, this is the way we can calculate the rth arbitrary moment of a random variable if the moment generative function is a variable and if it is differentiable with respect to t. And here we are finding the what is the first arbitrary moment. So, first arbitrary moment mu 1 dash, how do you find the mu 1 dash? You know the value mu 1 dash, but we are finding the value of mu 1 dash using the moment generative function. So, mu 1 dash is equal to derivative of the moment generative function with respect to t when t is equal to 0. That is our first arbitrary moment. And we have the moment generative function mxt. This is equal to e power lambda into e power t minus 1. So, you differentiate this moment generative function with respect to t. You are differentiating this moment generative function with respect to t. This is an exponential function. Use the derivative of an exponential function. This is a function of function rule. Using that function of function rule, this is the derivative of x, the derivative of x is e power x. So, derivative of this function lambda into e power t minus 1, we are differentiating with respect to t, remember, lambda e power t minus 1, but this is a function of t, this is a function of t. So, into the derivative of that function, the derivative of that function is lambda into e power t. So, we have the derivative of the moment generative function with respect to t is equal to e power lambda e power t minus 1 to lambda e power t. What about this value when t is equal to 0? You just identify the value of the first derivative of the moment generative function when t is equal to 0, that is derivative of moment generative function with respect to t when t is equal to 0. You just note here e power lambda into e power t is here 0 minus 1 into lambda into e power 0, and that is equal to e power lambda into e power 0 is 1. So, 1 minus 1 into lambda e power 0, and so that is equal to e power 0, this is actually e power 0, that is 1, this is lambda, again this is e power 0 1. So, this is equal to lambda. So, what we obtained, if we are differentiating the moment generative function of the Poisson distribution with respect to t and put t is equal to 0, you will get the value as lambda, that is mu 1 dash is our value, that is equal to lambda. Already we derived this mu 1 dash using the usual practice of derivation of mean and variance, mean arbitrary moments, mean and other arbitrary moments. But here we are finding the mean using the moment generative function, and suppose you are finding the second arbitrary moment using the moment generative function, we have to differentiate the moment generative function 2 times with respect to t, second derivative, you find the second derivative, this is the first derivative, see this is our first derivative, and again you differentiate, you will get. So, suppose derivative of mx, derivative of the moment generative function we obtained as e power lambda e power t minus 1 into lambda e power t. This is the derivative we have, and second derivative you are finding the second derivative of this with respect to t. Suppose you are finding the second derivative, this is equal to, again this lambda, if you want, lambda is taken outside, common factor, and this is product of 2 functions of t, first function this one and second function, this is our first function and this is our second function, and using the derivative of the product of 2 quantities, you have the first function, that is e power lambda e power t minus 1 into derivative of the second function. Derivative of the second function is e power t, derivative of e power t, that is e power t itself, plus derivative of the first function. What is the derivative of the first function? E power lambda e power t minus 1. Since it is a function of t, you have to multiply the derivative of that function lambda e power t, okay, into the second function. What is the second function? E power t. Okay, I think you understand. That is, when we have the first derivative, you consider this is our first function and this is our second function, and so this is the first function into derivative of the second function plus the derivative of the first function into the second function. So, this is okay. So, this is the value, and we are substituting the value of t is equal to 0 here also. So, when t is equal to 0, what are the modifications we have? When t is equal to 0, you just find what are the values. This is equal to lambda into e power lambda into e power 0 minus 1 into e power 0 plus e power lambda into e power 0 minus 1 lambda into e power 0 into e power 0. So, when t is equal to 0, these are the situation, and that is equal to lambda into, this is e power 0, because e power 0 is 1. So, 1 minus 1 0. So, e power 0, that is 1, this is 1. So, 1, this is e power again 0, e power 0, that is 1, lambda 1 1. So, lambda. So, what is the second derivative? The second derivative d square m x t divided by dt square when t is equal to 0 is equal to lambda into 1 plus lambda, or we can write lambda square plus lambda, and this is our mu 2 dash, and this is already we derived using the usual practice of derivation of the arbitrary moment. But here we derived the second arbitrary moment based on the moment on the basic based on the derivative of the moment generative function. So, similarly you can find any arbitrary moments of the Poisson distribution by finding the derivative of the moment generative function and put t is equal to 0 corresponding to that. And so, and again come to the point of Coumadin generative function, and we have the definition of the Coumadin generative function, that is kappa x t is equal to log m x t. You know that. The Coumadin generative function kappa x t is a logarithm of m x t. This is our Coumadin generating function. We have the Coumadin generative function log m x t, and for the Poisson random variable, this is logarithm of, already we established that moment generative function is this one, logarithm of e power lambda e power t minus 1, or that is simplifying, you have lambda e power t minus 1. So, remember, for a Poisson distribution, the Coumadin generative function is equal to lambda e power t minus 1, and since it is lambda e power t minus 1, lambda in e power t minus 1, you can see how we can find the Coumadins of the distribution. Very simple, the rth Coumadins are given by the coefficient of t power r divided by r factorial in the expansion of kappa x t, and already we have, this is the orthocombinant. We can find the orthocombinant by identifying the coefficient of t power r divided by r factorial in combinant generative function. And combinant generative function is a very simple expression for the Poisson distribution, and it is very convenient to expand that combinant generative function also as a power series of t, because kappa x t we have already obtained as lambda into e power t minus 1, and see what is the expansion of e power t. You know the expansion of e power t as this one, 1 plus t divided by 1 factorial plus t square divided by 2 factorial plus etcetera, and that is minus 1. So, this minus will be cancelled and the remaining factor become lambda into t divided by 1 factorial, t square divided by 2 factorial plus etcetera. Hence, from this expression, it is very interesting to note that the covariance of the Poisson distribution, that is our coefficient of t power r divided by r factorial. You are finding coefficient of t power r divided by r factorial in the expansion of the combinant generative function, and what is the coefficient of every t divided by 1 factorial, t square divided by 2 factorial, t cube divided by 3 factorial, whatever be the expression, the coefficient is actually lambda. So, that means kappa r is equal to lambda for every r. Kappa r means the kappa 1 is equal to lambda, kappa 2 is equal to lambda, kappa 3 is equal to lambda. So, you just note a very interesting property for the Poisson distribution. All combinants of Poisson distribution are equal to lambda. So, for a Poisson distribution with the parameter lambda, you note that all the combinants of the distribution are equal to its parameter value lambda. And after deriving the moment generative function or the characteristic function, we are in a position to derive another property, a characterization property of the Poisson distribution, that is additive property. Suppose you are given independent Poisson random variables, then what can you say about the sum of the independent Poisson random variables? That sum is also a Poisson random variable. That is, suppose you are considering two independent Poisson random variables x and y with the respective parameters lambda 1 and lambda 2, and then x plus y is also a Poisson random variable with the parameter sum of the parameters. And how we are establishing this additive property, and we can establish this additive property using the moment generative function technique, because we know for a distribution, if you identify the moment generative function, that using the moment generative function we can uniquely determine the distribution. So, you find our aim is to find what is the moment generative function of x plus y. Let me derive this moment generative function of x plus y. Suppose x follows Poisson with lambda 1, then moment generative function of x is e power lambda 1 into e power t minus 1. Similarly, y is Poisson with lambda 2, then m y t is equal to e power lambda 2 into e power t minus 1. Remember, this x and y are given as independent. X and y are independent random variables. If x and y are independent random variable, you are finding the moment generative function of x plus y. So, suppose you consider MGF of moment generative function of the sum of random variables x plus y, that is m x plus y t, and using the property of the moment generative function, you know moment generative function of sum of two random variables is equal to product of the moment generative functions if x and y are independent. So, this is equal to m x t into m y t. Since x and y are independent, and this is equal, substitute the earlier expressions, we have so that is the moment generative function of x with x, that is a Poisson random variable with the parameter lambda 1, y with the Poisson random variable with the parameter lambda 2. So, these two moment generative functions are substituted, and you can combine those factors and written as or that is e power lambda 1 plus lambda 2 into e power t minus 1. Because e power t minus 1 is common in two factors, you take it common factor e power t minus 1, then the remaining factor is lambda 1 plus lambda 2. Just note this expression. This expression is actually, that is, we have the moment generative function of x plus y t we obtained as e power lambda 1 plus lambda 2 e power t minus 1, and that is equivalent to e power lambda into e power t minus 1, where lambda is our lambda 1 plus lambda 2. So, this is the moment generative function of a Poisson random variable with the parameter lambda. Hence, by uniqueness property of the moment generative function, this random variable x plus y is nothing but a Poisson random variable with the parameter lambda, and that lambda is our lambda 1 plus lambda 2. So, this way we can establish sum of two independent Poisson random variable is again a Poisson random variable. We can generalize this property for an independent variables. Suppose x I follows Poisson with lambda I, where I is equal to 1, 2, etc. up to n independent Poisson random variables. These are independent Poisson random variables. Then what can you say about sum of the random variables? Sigma over I is equal to 1 to n x I. This is a Poisson with the parameter, sum of the parameters. So, that is, instead of we have, these are the additive property with respect to two random variables, and this is the additive property with respect to n random variables. So, generally, suppose we have n independent Poisson random variables, sum of n independent Poisson random variables is equal follows Poisson distribution with the sum of parameters. And now, one example, let me give one example with respect to this additive property. Suppose you consider x, this is a Poisson random variable with the parameter 2, and y, it is a Poisson random variable with the parameter 1 by 4. Then can you find probability of x plus y is equal to 0? This is a question, or whatever be the probability values required, you can find, or what the mean, if suppose you have to find the mean of x plus y or variance of x plus y, you can find using the additive property. How it is possible? That is, you are given x follows p with the parameter 2 and y follows p with the parameter 1 by 4, and they are independent. And because of the additive property, you can write this x plus y follows Poisson with the parameter 2 plus 1 by 4, or that is x plus y follows Poisson with the 9 by 4 or 2.25. that is x plus y follows Poisson with 2.5. So, if x is a Poisson with the parameter 2 and y is a Poisson with the parameter 1/4, we have using the additive property x plus y follows Poisson with the parameter 2.5. And the question is, what is the probability of x plus y is equal to 0? This is our question. If x plus y is a Poisson with the parameter 2.5, generally you can write x plus y is equal to some, suppose some k. This is equal to e power minus lambda power k divided by k factorial. And here this is k is 0. So, this is e power minus lambda power 0 divided by 0 factorial, or that is e power minus lambda, and lambda is equal to 2.5. So, this is equal to e power minus 2.25, and e power minus 2.25 is approximately equal to 0.105. So, this is 0.105. That is, if you know the character of the random variable x, that is Poisson with the parameter 2, and the character of the random variable y, that is a Poisson with the parameter, another parameter 1/4 say, and these are independent, we can find the probability values corresponding to some of the random variables, or we can find the mean of the sum of the random variables, or we can find the variance of the sum of the random variables, etc., using the character that sum of the random variables, sum of the independent Poisson random variables follows Poisson distribution. So, with this we can wind up this session. Thank you for listening this session, and we will again discuss some more properties with regard to Poisson distribution in the next session. Thank you once again.